Let's talk about something you see literally every single day, but probably don't think twice about. That tiny little lock icon up in your browser's address bar. It's the symbol that tells you a website is secure, but what does that even mean? Today, we're going to crack it open.
Right? You see it all the time, you trust it with your passwords, your credit card numbers, but what is it really doing? It's not just one single thing. It's this incredible, lightning-fast, multi-step digital handshake. So let's dive in and see how it all works.
To really get why we need that lock, you have to understand a fundamental, kind of scary truth about the internet. By default, it's basically a postcard. Anything you send, an email, a password, whatever, is written in plain text for anyone along the route to just read. There's no privacy built in.
So how do you fix a postcard problem? Well, you stop writing in plain English. The very first step is to create a secret language, a code that only you and the person you're talking to can understand. This whole idea is called encryption, and it's job number one, confidentiality.
The fancy, official name for this system is a crypto system, and it's actually a pretty simple idea. It takes your normal message, that's the plain text, and uses a secret key to scramble it into something that looks like complete gibberish. That's called the ciphertext. And that secret key, that's the magic ingredient. It's the only thing that can unscramble the message and turn it back into something readable.
So the flow looks just like this. You've got your message. You use a key to lock it up. It becomes a jumbled mess. And then on the other end, the receiver uses their matching key to unlock it and get the original message back. Simple, right? But without that specific key, that scrambled message is just useless noise.
Okay, so we're talking about keys, but it turns out not all keys are created equal. There are really two main ways, you could call them two different dialects, for handling these secret keys. And each one has its own major pros and cons.
So on one side, you have symmetric encryption. This is the speed demon. It's incredibly fast because it uses the exact same key to both lock and unlock the information. But there's a huge catch. How do you get that one secret key to the other person without somebody else stealing it? It's a classic chicken and egg problem. Then you've got asymmetric encryption. This is clever. It uses two different keys, a public key that you can share with the whole world and a private key that you guard with your life. This solves the sharing problem, but man, is it slow. Like really slow.
So what's the answer? You're faced with fast but risky versus slow but safe. Well, the solution is just brilliant. You use both. This is the hybrid approach that makes the modern web work. You use the slow, super secure asymmetric method for one tiny little job to safely exchange a brand new, one-time use secret key. Then, once you both have that key, you switch over to the blazing fast symmetric method for the rest of the conversation. It is absolutely the best of both worlds.
All right, so our message is secret. That's awesome. We've solved the postcard problem. But that's only half the battle, isn't it? How do you know the message actually came from your bank and not some scammer? And how can you be sure that no one's messed with it on the way? This brings us to the next part of the puzzle, proving who you are.
And the main tool for this job is something called a hash function. Just think of it like a digital fingerprint generator. You can feed it anything, a single word, a whole book, an entire movie, and it will spit out a unique, short string of letters and numbers. That's the hash, the fingerprint. And it's a one-way street. You can never ever take that fingerprint and figure out what the original message was.
Now, for a hash function to be secure, you need to be sure that two different messages can't create the same fingerprint. That's called a collision. To get why this is so important, let me ask you a kind of weird question. How many people do you think you'd need to get in a room to have a 50-50 shot that two of them share a birthday? What's your guess? Maybe 183, half the days in the year? 100?
The answer, and this is going to blow your mind, is just 23. 23 people. It's called the birthday problem, and it's a famous statistical quirk. This is exactly why we need our hash functions to be so strong. A clever attacker could use this same logic in what's called a birthday attack to try and create a fake message that has the same digital fingerprint as a real one. It's why modern security uses hash functions that produce super long fingerprints, making a collision like that basically impossible. So here's how you put it all together to create what we call a digital signature. First, the sender hashes their message to get that unique fingerprint. Then, and this is the really clever bit, they encrypt only the fingerprint with their own private key. That encrypted hash is the signature. When you get the message, you use the sender's public key to unlock the signature. If the fingerprint you reveal matches a new fingerprint you create from the message you received, bam! You know two things for sure. It absolutely came from the owner of that private key, and the message hasn't been changed by even a single comma.
Okay, we are so close. We've got a secret message, we've got a verifiable signature, but there is one final, absolutely critical piece missing. How do you know that the public key you're using to check that signature actually belongs to your bank? What's to stop an imposter from just shouting, "Hey, here's my public key," and tricking you?
And that's the core lesson here. You just can't trust a key that you get from an anonymous source online. It's just not secure. You need a system of trust. You need a way to verify for sure that a public key is tied to a specific identity. In other words, you need certificates.
And this is where a certificate authority, or a CA, comes in. These are big, trusted organizations whose entire job is to be like a digital passport office for the internet. A website owner has to go to them and prove who they are, and in return, the CA issues them a digital certificate that officially binds their identity, like www.mybank.com, to their public key.
So what's actually inside one of these digital passports? Well, it's all the important stuff: who the certificate belongs to, what their public key is, which CA issued it, and how long it's good for. But here's the most important part. The whole certificate is digitally signed by the CA itself. Your web browser comes preloaded with a list of CAs it already trusts, so it can check that signature, trust the certificate, and then trust the public key inside it. It's a chain of trust.
So let's bring it all back home. That little lock icon, it's not just one thing. It's this whole symphony of technologies working together in perfect harmony. It's a hybrid crypto system to keep your data secret. It's a digital signature to prove who sent it and that it's unaltered. And it's a certificate from a trusted authority that acts as the notary for the whole deal. It's a team of tools, all performing that secret handshake in the blink of an eye.
The system we've just walked through is incredibly powerful for the computers we have today. But technology never ever stands still. The very math that makes all of this work is being threatened by the incredible power of quantum computing. And that leaves us with one big question for the future. How long will today's secret handshake be able to keep us safe? And what will the next one look like?